Hello everyone, this is Avinash again presenting you a steady state visual evoked potential. I am from Center of Artificial Intelligence, University of Technology, Sydney. So let's see what is a steady state visual evoked potential. Before we go in more deep, we should understand what's a visual evoked potential itself. So visual evoked potential, like the terminology itself telling you, it happens whenever we see any object by our eyes, certain signal generate in that part of the brain shown here in the red. This signal is known as a visual evoked potential due to this image shown to the user. Of course, this terminology is for EEG devices, not other devices. In case of other devices, the terminology changed for them. This backside of the brain is known as a occipital lobe. So what is steady state evoked potential then? Let's see let's see again how visual evoked potential reach to the steady state visual evoked potential. So visual evoked potential can be divided in two parts. One is a transient visual evoked potential, for example P300 shown in the previous slide, which occur whenever user presented with a rare stimulation, and such rare stimulation generate a P300. For example, in this picture, U is that event which need to see or find out with other letters, and that is a rare compared to other letter in mostly around 25% to 75% ratio. Such kind of visualization to the user, stimulation to the user, is known as a transient. But on the other hand, if we present a user a certain flickering visualization like presented here, then he presents several such peak you can see in here. This several such peak is always close to the same amplitude and usually known as a steady state visual evoked potential. So that's where the SSVEP come from. Let's see more formal definition of SSVEP. SSVEP are the signal which are natural response to visual stimulation at a specific frequency. This phenomena, like I told you earlier, is a visual evoked potential, so happen only in EEG. Although it can also measure with MEG devices, but those is not visual evoked potential, but it become visual evoked fields. If we replace the visualizations of visual stimulation with audio stimulation, then the same SSVEP changed to a steady state auditory evoked potential, but again measured by EEG. But if we change to MEG, it's again become visual evoked fields. So for example, this picture I've shown in the previous slide. Let's assume this picture is at 10 Hertz. And if you staring this picture for a while, let's say about 2 seconds, and the signal gathered from this picture from the occipital lobe feed into fast frequency transform FFT, then the output which will look like this. You will see at 10 Hertz as well in the signal. And of course, the following repeated pattern of the 10 Hertz, 10, 20, and other 10, 30, 20, 30, 40, 60 Hertz. So this is the phenomena which is occur with SSVEP every time you play with that. Let me show an example how SSVEP working. So this is the game, a Tetris game played by SSVEP. In this game, user presented with 4 SSVEP options you can see, which let your Tetris object able to turn in certain direction. User need to stare in certain choice of SSVEP turning point so that his object turn and he get the score. So this is a nice example what BCI can does with the help of SSVEP. So the question arises, is it easy like we saw in this video? Was it a really good BCI tool? Is it a really good BCI paradigm? So let's see the pros and cons of SSVEP in terms of BCI. Like I have shown you in the picture, in the video earlier from this slide, it doesn't require any training, which is very, very useful when you're developing a BCI system. So it's independent of user pretty much. And you don't need to collect data from every time a user come in or participant come in the lab. Our system need to be used by certain different user. It comparatively from other BCI paradigm is a bit more robust toward noise, which is another one very important phenomena and very important property. It also have higher ITR, information transfer rate. User can communicate comparatively faster than other BCI paradigms. For example, they can communicate several words within some seconds. And the more importantly, because it have less noise, that also means the signal to noise ratio is also higher. So quality of signal is improved overall. Even though it has lots of nice property as SSVEP, there's a certain problem as well. The problem starts with the limitations of frequency you can present to the user. If this frequency go beyond, then the user will not have any SSVEP phenomena. And these frequencies usually lie from 3.5 Hertz to 75 Hertz. And the top, which I haven't mentioned here, there's also limitation in terms of hardware, how much you can show. Well, second important point, which you already might realize, that if you're staring that kind of flickering for a while, it's not comfortable at all to use, right? So that's actually put everything down because it's not comfortable at all. If it's not comfortable at all, then how we can make it as a BCI system, right? Well, next thing is, if you're presenting that on the monitor, like I just presented you, it depends on if your monitor have good brightness, good light, good color or not. And also more importantly, it's also depend on refresh rate of your monitor, which is more of technical issue, but it really have high dependency. It's vary a lot from one monitor to another monitor when you develop a system. Last but not the least is size of the stimulus itself. If let's say if I make a whole screen as a one stimulus, the effect will be very high. But if you make a smaller square or rectangular size stimulus, very tiny all over the screen, bunch of them, maybe the effect will be very, very little. It also has been seen that by age, the effect of SSVEP decrease, and more importantly, participants need to pay attention toward SSVEP to make them react toward whatever user want to do. So if you don't have this kind of consideration while developing a SSC-based BCI, the system is promising, but still not promising. So let me give you one nice example of one of the BCI system which I work on in the past. It's called SSC Based Assistance system. Basically what it does, it develops for disabled people who have limited mobility to control a computer to have different kinds of assistant for them. For example, they can have food with the help of a robot. They can watch certain entertainment programs or have entertainment. They can even call their family member, that kind of functionality. But again, this is just a command you issued from SSVEP, and you can extend to different variety of possibility. The system is pretty much look like this, presented in this picture here. The system contains a EEG system, a big screen with bunch of stimuli for SSVP, and this whiteboard is a plastic meal box which have lots of blocks in there, and this water bottle, and of course there's a robotic arm and other emergency thing, and there's a somewhere in the corner there's a computation unit which is CPU to process this whole thing. So a basic BCS system, what basic BCS system required, SSVP system required pretty much same kind of mechanism to work on, to develop on. So the architecture of SSVP BCS system is not much different from other standard BCS system presented in the beginning of presentation, right? So again, you also need a stimulus, which in this case is a monitor with lots of flickering stimulus on the screen. So if you don't have that stimulus, which is also known as a BCI paradigm, of course, the data collected by you doesn't have any meaning. You need this context. You need this kind of phenomena to occur. If you want phenomena to occur, of course, you want to collect those signals. So that's the number 2. So you need to acquire signal from the stimulus. So in this case, because it's SSVP, what you're seeing here is a MINDO device. It's a wireless dry sensor EEG device, where the 2 sensors touching his occipital lobe. Somewhere around, it's a bit higher than occipital lobe, but yes, there is. And of course, once you have stimulus and you have signal acquisition, you need to process those signals, right? And this is a real-time system, what I'm showing you here. So this process signal need to classify in the real time as fast as possible. And once you're able to classify the signal, you get the answer, what frequency user is looking at. You can actually issue a command and perform an action, right? So this is the number 4 thing. In this case, it's a robotic arm or certain in other interface in the screen, on the screen for the user. So what problem basically we are solving in SSVP based BCI? What are the machine learning point of view? What are the problems here? If I define that way. So the core problem in SSVP based BCI system is to detect the frequency of SSVP component EEG signals, right? So what we want to do, we want to detect the focus frequency where user is looking at. How we do that, I already showed you in the earlier slide that FFT can show you the peak. So why not we just find that peak for the user so that we can convert it in the command, right? So if I define in formal way, now let's say there's a K stimulus frequency from F1 to Fk shown to the user, acquired from n different EEG channels over the L second. Then the objective for a machine learning researcher should be how we can find the maximum frequency among all those frequency users looking at. To do so, one very, very popular technique specifically in SSVP domain is canonical correlation analysis. It's very simple technique which is making sense by cross covariance matrix to find underlying correlation between 2 sets of different signals. So once you have 2 different signals, one is basically a signal you're acquiring from the user every second or every minute, depending on how long you want a trial, compared to the standard signal. One important thing I forgot to mention here is that because you have a context about SSVP based BCI, so you know which frequency you are presenting to the user. Those frequencies are always known, it's not unknown frequencies. What you need to find that which frequencies user is looking for from the set of frequency you provided him to watch. If you see from this diagram, what we need to do, machine learning point of view, that take those X signal recorded from multi-channel EEG device And for each those signals, specifically we focus on occipital lobe and see their CCA, canonical correlation analysis, with a referred signal Y, which is presented for the certain frequency. And we do this for all the presented frequency. Let's say there are K represented frequency, and find out which one is a maximum or which one has the highest canonical correlation analysis. Of course, this is the ideal condition. You will not always find a one maximum. Maybe you find two very equivalent frequency, and it's very difficult to choose which one is correct, which is not. That's where the quality, signal to noise ratio, and other phenomena kicks in. So, however, this system can work pretty well with CCA, but still it faces lots of issue in terms of how long trial required to have better performance, right? So if you see in this figure, as the data length, basically a trial length before you make a decision using CCA, larger the trial length, larger the data length, is better the accuracy, which go up to 92.13% to detect the right frequency, focused by the user to perform certain action, right? But 7 seconds is too long to get that higher accuracy, because user need to sit for 7 seconds so that he can perform another action. It might be good if he performing certain action which doesn't require very quick reaction, but it will be very slow. For example, he want to talk with someone, so he can talk for one word or one letter every 7 seconds. This is definitely not good. So that's where more research required, more machine learning work required to improve this certain data length requirement. Usually we measure this in terms of information transfer rate. Those who don't know, is a measurement to find out that how much bits per minute communication is possible using a BCS system. And like you see here, it highly depends on the accuracy, of course, and the most important part is the stimulus duration in second for selection of that object using BCI paradigm. In this case, it's SSVEP. So if we go back to the figure, this is so 7 seconds is too high that ITR in this case must be super high as well. And of course, we don't want that. We want that it will be lower. So if we can able to lower the T, let's say less than 1 second, maybe 500 milliseconds, then the ITR will improve significantly. But usually in that case, P, which is accuracy, deteriorate a lot. And of course, the number of targets. So balancing these three factors is so difficult. But of course, development of niche machine learning technique able to help us to improve this frequency, this SSVEP performance a lot. It's not just applied to SSVEP, of course, like I mentioned, it's general for all BCI paradigm. And yeah. So let me show you another full example of what I have shown you before of SSVEP. So you are seeing here that the participant need to see different options. He can focus on the required option he's interested in. So in this case, he's looking at 5 options, and all 5 options showing him different option of food choice, including the water and going back button. He have chosen certain food choice. You can see selected in blue color, and that robot arm get a command and take the food and feed to the user. That's a nice demonstration of actually a brain-computer interface, that what is possible with SSVEP paradigm. An important point is here is that someone who cannot move at all, have very limited mobility, such mechanism is very, very helpful for you. Of course, there's a discomfort to see this flickering all the time, but for someone who cannot do anything, for someone with disability, it's still better than nothing. But of course, we don't want that he still suffer from flickering point of view. That's why we also want that it should have higher ITR rate. The user just need to see the flickering for like 500 milliseconds and he can have detected command, and that command performs certain actions, right? That's what we want. That's what we wish for. And you see user selected here the water glass option, and that's robotic arm, which is very precise, defined arc where to move, provide the user the option. This is just demonstrations. Of course, you will see user could not even drink the water enough, and the robot already pulled back the choice of glass. So, but this is the example which showing you that what is possible with one simple SSVP paradigm. We also have some other option of entertainment where you can choose different choice. So again, he's choosing the feeding option. Maybe he's hungry too much. So we have SSVP, we know the paradigm, we have some basic methodology to detect those commands produced due to SSVP from the occipital lobe using the EEG signal. Even though there's a lot of open data set available, some of the famous one is SSVP data set from Information Technology Institute and UCL Machine Learning Repository. And there are also lots of other data sets from Tsinghua University and Professor Hovijim Beckert, GN. But this is just a source. I'm showing you some of the data set, but there's a more available. Sometimes it's not easy to find, but there's always more available data set out there. But there's a big problem, even though you have data set, right? What is the problem? Okay, I'm a cognitive neuroscientist. I know I have a domain knowledge about SSVP, about the brain. I have understanding what is going on in the brain, how the signal is collected. Because of those context information, because of those domain information, I know whenever I see a new data set openly available, how I can run it, how I can process it. But a person who is more machine learning researcher, you want to use this data set to improve the performance of SSVP based BCS system, he will face several problems. Some of the problems are like different information which he need to dig out from the data set. For example, channel, how many channel has been used, what are the sample frequencies used, what is the frequency of flickering and how many such frequency are there, how the scenario look like, what's the trial duration in the data set. If there's a notch filter of 50 Hertz, 60 Hertz, is highly depend on the country of the data set collected, and reference electrode. This information are easy to dig out by people who are domain expert, but not easy for people who are not domain expert, like a machine learning researcher, who are not really focused on brain signal itself. Second important factor came in the scene is a file format. So if data is arranged in separated by participants, separated by trials, and of course, more importantly, what kind of extension dataset contain, so that you need to download certain tool so that you can read the dataset, right? So, and the last but not the least, that how if dataset already has been pre-processed, if the pre-processes already happened with the dataset, what kind of bandpass filter has been used, if data is resampled, that kind of information. So you see, it's a bunch of information required. bunch of preparation required before you can read that data set and do something with that. And the problem is that even though you learn from one data set how to do that, you cannot easily apply same phenomena, same logic, same program piece of the code you have to different other data set you download from different source. And the problem is that they are not following the same pattern. They are not following the same standard to store this information for the user who want to download and use the data set. So this brings us to the point that even we want to improve the performance, there's a lot of work need to be done. First is to make the data sets available openly for the use, for the researcher like you in the unified standard format. In the format that you just can develop a one single interface in your code and read the data and just more focus on your algorithm to improve the performance, rather than you focus on to process the data from one format to another format, you dig out different information from the data, and then you push some time on your machine learning. So basically you are you are reducing the machine learning work in some way, and because of that. So what we can do, the one thing we can do, we also be doing as a IEEE P2731 IEEE committee member, that we're trying to propose this unified standard to the public, which you already heard in previous slides. So in conclusion, we need something which is more unified, which is following more standard. But why we need those things? Because we also want that you improve the performance of the system in the way that it can have higher information transfer rate. Because if it have low information transfer rate, the system is also not very useful in SSVEP kind of BCI paradigm. But again, it's applicable to pretty much any kind of BCI system available out there, right? So of course, like I mentioned earlier in the slide, SSVEP could be a good choice for BCI application. Why? Because it doesn't require training. It's independent of user. Of course, it has some dependency on the age, but still it's comparatively very quick to start by user and start playing around with that. Second, although it's a good choice for BCI application, but the performance and IT are still low, and we need more researcher like you to improve this performance. So we need this system to have high performance and, more importantly, higher information transfer rate. It needs to make users feel more comfortable to interact. I'm talking in terms of real-time system, but of course offline you can do a lot of more things. But once you develop the algorithm offline, then only we can use it online manner in real time. And the next, which is very, very important, is specifically someone who doesn't have domain knowledge, to have unified standard of data representation, which can overcome the gap between machine learning research and cognitive neuroscientists, of course. If we can have more standard by people who are sharing open data, you are also easy to use it easily without spending a lot of time to learn, understand, and process the data before you can focus on your machine learning algorithm, right? So that's actually important part also required when we are talking about unified standard. So these are 3 takeaway points from me in this SSVEP. Thank you, and I hope you like it, and feel free to ask questions. Thank you.